Right. Frames up. So yeah, we're gonna get started with day 2 now, which we're gonna be. So forces. I mean, everyone knows the definition of a push or a pull. And forces are, of course, going to be a vector since you can push in any direction you want to. And you'll normally see in a diagram or something, you'll see forces labeled by an F with some sort of subscript describing what type of force it is, like friction or just the force of a hand. And you'll also see an arrow on top of this F sometimes because it's a vector, and that's just how you represent vectors sometimes. You don't really see this as much for like velocity, but you will see it sometimes. You'll just put an arrow on top of your symbol to show that's a vector. And importantly, the net force is basically the sum of all forces acting on the object. And remember, in vectors, like direction matters. So if you have 2 newtons pushing right and 2 newtons pushing left, then that's going to be 0 net force, not 4. So going over some common forces, these are probably going to be, you'll probably see these as the most common forces as in the course and just in general. So you have your generic, just random force caused by something, like you pushing something or something along those lines. This can be considered a normal force, which we'll explain later, but for the purposes of actually doing physics problems, it'll just be like something like F hand or F box or something like that. So friction, which is why we cannot infinitely slide across the floor, and is caused by 2 objects touching each other and sliding against each other, basically. And these forces will be pushing opposite of the direction of motion. And the friction force will occur at the location that the objects are touching. So if you're sliding forward if you're just like sliding forwards, the floor will produce a backwards friction force on you. But also your feet will be producing a forwards friction force on the floor because you're going to be sliding forward, and relative to your feet, the floor is moving backwards. So your feet are going to exert a forward friction force on the floor, although obviously you're not going to drag the floor with you on a slide. The floor is going to drag you to stop. And of course, this is going to create sound and heat. As you've seen like sparks fly off of wheels, gears, and all that. And normal force now, which is basically why you do not fall through the floor and just sort of descend to the bottom of the earth. And it's just 2 touching objects pushing against each other to not clip into each other. You cannot no-clip your walls in the real world. And gravity. I'm sure everyone here knows what gravity is, so I'm not going to. You'll go over gravity more specifically and like how gravity works on like planets and stuff in a later unit, but that's not exactly relevant at the moment. Just know that gravity exists and it's going to be its own type of force. Next is drag or air resistance. You'll see it referred to as either. Typically in the phrase, assume air resistance is negligible or something along those lines. Basically, it's just air friction is the best way to think about it. Just friction with the air particles as you fly. And this also prevents you from achieving ridiculous speeds by jumping off the top of the Empire State Building or something. You cannot reach 5 billion miles per hour by falling very far. Unless you're in space, I guess. But at that point, it's hard to do that kind of stuff. Anyway, this point's opposite the direction of motion. So it's, like I said, air friction. And you don't have to calculate this in this course. You will never have to actually calculate air resistance. You'll go into this in AP Physics C if you decide to take that course, where calculating how air resistance actually works will require calculus. You'll have to recognize that it exists and like draw which direction it's pointing on sometimes. but that's the full extent of what you're going to be using air resistance for. You'll also just sometimes straight up not have this in most physics problems to make the calculations, appropriate for the level of this course. Moving on. So tension, typically represented by Ft or something along those lines. And it's just the string pulling on an object, like some sort of rope or anything like that. And this will always be pulling in the direction of the string with the same tension on both sides of the string. That's something important to keep in mind. And the tension, the actual value of the tension is how hard it's pulling on one side of the string. So if you're pulling on a rope that's attached to the wall with a strength of 5 newtons, the rope's going to be pulling on the wall, and you're not moving, obviously, because, it's attached to the wall. You're going to be pulling on the string with 5 newtons, but the wall's going to be pulling back on the string with also 5 newtons, which creates a tension of 5 newtons overall. But that's not 10 newtons because both sides have a 5 Newton force. It's only the one end that actually counts for tension. Oops. That sent me back to start for some reason. Right. So next is spring force. It's the force of a spring. And basically what this is springs want to exist at like a certain length. You can push it in or you can pull it out, but it'll always try to go back to one specific length if you just leave it alone. So this force is basically just pulling, it's the spring pulling back to its natural length, which is called the equilibrium length. You'll go over springs more in depth in like unit 4, I think. Yeah. But there's a couple others I didn't really mention here. There's a thrust, which, rockets, if you shove a bunch of fire out, well, technically just hot gas, out the back of the rocket, you get pushed upwards. And magnetic force is also not included here, mostly because that's not going to be relevant for this course. You'll see that in, Physics C. But that's not going to be for this course. Obviously, magnetic force, it gets kind of complicated. So Newton's laws, I'm sure you've heard of them. There's 3 of them, obviously, and these are what define classical mechanics. And there are other models. You're not going to learn these for a while. Those are probably going to be like college courses. But for the purposes of high school physics, these are going to be the basics and what defines like the entirety of mechanics that you're going to be looking at. So these have a lot of common mistakes, and they like to just straight up ask you about Newton's laws and just make sure you know what you're doing with them sometimes. So be on the lookout for those questions on the AP exam, or just tests in general, because physics teachers do want to make sure you actually understand what Newton's laws mean. So going to the first law, which is probably the most boring one. I'm sure everyone's seen like some version of this wording. This is just called inertia most of the time, which is basically if you leave an object alone as it's doing whatever it wants to, it will keep doing that whatever until you force it to stop doing whatever. So if a ball is flying through space, it will keep flying through space until it gets caught in a black hole or something like that. This is also why it hurts to get hit by a truck, because the truck will attempt to continue moving, and the external force that stops the truck from moving at full speed is going to be your body, and that hurts. And of course, you don't actually see stuff floating off into the distance in the real world. You have air resistance and friction, which act as external forces to, prevent being in motion forever. Perpetual motion machines do not exist yet. So Newton's second law, this is going to be the most important one. Never forget this. You probably won't be able to forget it. You will see this everywhere. And it's F equals ma. It's literally just the equation. And some more units, because these weren't in 1D kinematics, obviously. You'll use newtons for force and kilograms mass, not grams. Never use grams for your standard unit of mass. It's like the odd one out, because you're using meters, you're using seconds. You're not using grams though. Don't use grams. And of course, this is technically net force. The force of gravity on our bodies is not causing an acceleration when we're sitting in a chair. It's going to be balanced out by the normal force of the chair, which means we're not going to fall through the earth. And yeah, so this is just something you should know. It's not exactly complicated. It's not hard to memorize. So just make sure you know this for whatever occasion you need it in. And do the third law, which a lot of people mess this one up. It's very easy to accidentally screw up. And this is your action has an equal and opposite reaction. And the actual specifics of what's happening here is if one object exerts a force on the other object will exert an equal and opposite force onto the first object. This is two objects acting on each other. This will not be two objects acting on one other object together, or one object acting on itself and something else at the same time. It will be two objects acting on each other with equal and opposite forces. And magnitude will always be equal, direction will always be opposite. You pushing on the wall is pushing on you back with the same force, even if nothing's moving. If you push a ball, the ball is pushing back with the same force, even if you don't get sent rolling backwards. Of course, the main reason stuff doesn't like always bounce off perfectly is because masses, F equals ma. So even if two things exert the equal force on one another, that truck is a lot bigger than you are and will not get sent back as much when you get hit by said truck. So yeah, very important law, but also one that's a little awkward to get right sometimes. It's good to like Google a few of these examples and make sure you are being clear. Questions like to get silly, and AP exams actually specifically this sort of question, like someone swings a baseball bat at a baseball and sends it flying with 10,000 newtons. What was the force of the ball on the bat during the swing? And the answer is just 10,000 newtons. There's not. This is just literal third law questions will show up on the AP exam. Never try not to miss them. It's you will see one of these questions. They show up in physics C2. It's a very basic law, but also one that you might just miss sometimes. Be very careful about it. So to make sure you don't miss these, there's a few things to run through your head to make sure, is this a third law situation? So once again, two objects acting on each other, a baseball and a bat colliding will have a force on each other. Two people pulling on a rope is, I'm glitching. Oh, is it like my voice or? I know the PowerPoint things the words, the sentence appear twice, but is something wrong with my voice? That's odd. Awkward. There's nothing wrong with my Wi-Fi right now, as far as I know. I'll try and speak a little slower then. That's weird. Nothing wrong in the house right now. I'll speak a little more slowly in case something messes up then. We have the time this time. There's no losing 17 minutes as a sort of class to a power outage. Anyway, fun fact, the power disappeared for like 2 hours, I think, yesterday. More than an hour and a half. It was like, yeah, all the transformers are going out apparently now. It's great state. We live in a great place. Anyway, so yeah, you have to have two objects acting on each other. Two people pulling on one rope doesn't count. What's something else that might get mistaken? Sort of think of a specific example at the moment, but like two objects pushing on each other. Gravity is an example of this. You might not think there's a third law pair with the Earth pulling on you, but there's a third law pair for every single force in existence. And you do exert gravity on the Earth. The problem is that the Earth is even bigger than the truck, and you're not accelerating the Earth very much at all. you have to make sure they're facing opposite directions, which can be a little difficult to truly make sure in the case of like weird collisions where you hit something at an angle. But with like normal force, and for example, right? The force will always be at the spot of where the objects are touching, and they will be pushing into the other object, and these will be based in opposite directions. If you can tell for sure, like if the problem gives you numbers that the forces are of different magnitude, it's not a third law pair. It's unreliable to use this by like an eye test though, because for example, like I said, truck hits you, the truck might not appear to take as big of a force, but you do in fact take an equal force from getting hit by a truck. So as for why forces are important, having being actual source of acceleration instead of just particle speeds up along a line. It makes problems more realistic. This type of thing that will actually show up on an AP exam of a particle moves at 2 meters per second. This is analyzing all the forces in an image allows us to actually find the acceleration and predict its motion. And like I said, F equals ma, big thing. I mean, there's literally a competition called F equals ma. And you'll be using this equation for a few years if you keep doing physics. So yeah, this is going to be one of the most important things to get down as one of the basics. Make sure you understand forces. F equals ma, don't forget it. And don't mess up your third law pairs. Every year. So free body diagrams. These are basically diagrams where you show all the forces on an object. You'll have like little arrows on your object pointing in the direction of the force. You'll have to draw a few of these on the AP exam most likely. And the exact length won't matter since there's no exactly a standard you can have for showing how strong the force is. But the relative lengths will probably matter, in which if one force is bigger than another, that arrow should be longer. And of course, if you add up all the arrows in a drawing or a diagram, you can get the net force. So these are a few examples. On this left, we have a box. Grab on a table. Gravity is going to be pulling the box into the table, while the table will exert a normal force back onto the block. That's going to be holding it. That's going to prevent it from falling through the table, obviously. And if you have a hand on the right, pushing left, that's the force of the hand. While the table will exert a friction force back on the block because they're touching opposite the direction of the force, which is pointing left. On the right, we have a pendulum. Tension always points in the direction of the string. You cannot point to any other direction. Gravity is obviously pulling it downwards, and air resistance is making it fall a little slower. Air resistance is kind of a weird one, though. You probably won't have to use it much. It's a lot of these other forces like gravity and normal force. If you forget to draw something like that, you might lose points. Something like tension or the force of a hand and its friction are generally not hard to try to identify in a situation. Oh God, what is? Okay. So yeah, if everyone understands this, I do have another Kahoot today because I don't create a slide to announce the Kahoot on accident. Anyway, I'll do the Kahoot and then we can see what people are kind of not doing as well. Because I remember yesterday there was a few problems when it came to displacement and the difference between that and just position or something like distance. So I'm going to go start this Kahoot, and then after that, I'll try to see if there's something we should focus a little more on. Let me go share the screen for this. Should be, yeah. All right. Free body diagrams are kind of hard to draw. So there aren't any free body diagrams here, but there are a lot of points about forces. Free body diagrams, you'll probably get a lot of practice with that in school. So I'll leave like a lot of the drawing practice. You can search up past AP exam FRQs that are publicly available on College Board website. And if you can find any free body diagram questions, you can go ahead and try to have some practice drawing those. I don't think the audio's on, but I can't fix that right now. Right. Yeah, I'm gonna wait for a number more people to join. Pins on the screen. Feel free to join when you want to. Yeah, because there's today more of an intro to free body diagrams. We're not gonna be drawing a lot of them today, but I do plan to like fish a few problems out of the past APs for tomorrow. And we'll be going over like just diagrams and graphs and all that tomorrow, a lot more into detail. So expect to see free body diagrams return tomorrow. And prepare to draw a few of them. Thankfully, these aren't actually complicated to draw. You don't have to like draw a hand or anything. The hand will be provided to you. Normally, you just have to draw the arrows. You probably won't ever have to draw anything that's not just an arrow. But yeah. Only 8 people in the Kahoot right now. Does anyone else want to join? All right, going once, going twice. Oh, okay. I'm gonna wait a little more then since it looks like people are still joining. All right, going once, going twice. All right, let's get started. Should be fairly straightforward. What type of formula we're using here? Oh, I put the wrong answer in the answer key. I'm so sorry. Yeah, it's gonna be yellow. I'm not sure how I accidentally hit the wrong one there. Yeah, so keep in mind, kilograms versus grams. This is yellow. I'm so sorry. How did I miss that? Anyway, yeah, so this is grams in the question, not kilograms. So you have to convert that into kilograms first. And of course, there's 1,000 grams in a kilogram. So the force is essentially going to be 1,000 times more effective. Oh, wait, no, that is correct. Sorry. Check myself. It is 4,000 because if you find the acceleration here, if you just find the acceleration, that's going to be 4 newtons divided by 2 grams. 4 newtons divided by 0.002 kilograms, which will give you 2,000 acceleration. So accelerate rate of 2,000 meters per second. But this is for 2 seconds. Timer might have been a little short, I suppose, but yeah, you'd have to like go through several steps. This might have been a little difficult of a question. So yeah, first, don't forget to convert to kilograms, and then remember to check what the question's really looking for, because it's not just asking for acceleration. Kind of forgot what was going through my mind when I made that question on accident. All right, I'm gonna try to answer this one a little more. Yeah. I think I did discuss this one earlier in class, so I expect most people to get this one right. Yeah, you do exert a force of gravity back on the Earth. It's just that the Earth is so much bigger that it basically means nothing. Almost everyone got that one right. I didn't put too many true or false questions. Don't worry. Yeah, just a basic knowledge test. Looks like we're understands this one. So this is just going to be looking at, whether you understand what the forces actually do. And consider that when we're walking, we're trying to move forwards. So what kind of force actually prevents from just walking in place infinitely? Yep. Drag doesn't work here because that's gonna be air pushing back against us as we walk, so that's not gonna help us very much. Normal force is gonna be the floor pushing up on us. So that's not gonna help us move forward very much. It might have like a slight forward component, but that's not gonna really do much. The real one here is gonna be friction, because as our feet push back on the floor to move, the floor pushes our feet forward, allowing us to hold our place and then move our next foot in front and keep walking. Great. Top 5 looking a little different. Going back to some more Newton's law questions. Yeah. Okay, remember, force is mass times acceleration. In this case, the cart is just sliding down the slope. We are not the sled is not accelerating. It's simply moving down the slope at a constant speed, which means there is no zero acceleration. So mass times acceleration, well, 2 times 0 is just 0. So yeah, you're gonna see questions like this every now and then. Make sure you don't get tricked. Remember, F equals ma is net force. If you're sitting in your chair, Earth's gravity is still very much there. You're not having zero force act on you by sitting on a chair. It's just that all the forces simply balance out and cancel, which prevents there from being any net force, which would actually cause motion. So the difference here is going to be no net force and no force at all. And those two are very different. Right? Everyone's seen like falling meteors and all that. They're going to catch fire. All right. Gravity is a good choice, but I'll go over why specifically on gravity in a bit. Friction applies to solid objects. If you're falling from orbit, you're not actually touching anything, so there can't be any friction. I did mention that friction creates heat and stuff, yes, but so does drag. Because once again, drag is just air friction. The force of the air on a falling object is what causes it to hit terminal velocity, and if it does that for long enough, it might create enough heat to have it just start burning. So that's why the answer is going to be drag here. And friction, once again, only solid objects. Don't put friction on a free body diagram if it's not touching anything. The law question. I think I did mention this example in class. It's hard to think of examples in the moment. Yeah. Looks like most people got this one right, at least. So going over the wrong answers first. Your hands exert friction on each other when they're rubbing. So your left hand will push against your right hand, but your right hand also pushes against your left hand. If two balls bounce off of each other, they're going to exert a normal force on each other, which is why they bounce. It's the normal force on the balls on each other. And of course, instead of two touching, they both have to exert the same force. A truck hitting you is another example of normal force, where the normal force of the truck on your body as you go flying is matched by the force of your body on the truck, creating a dent when you get run over by a truck. And of course, the correct answer, two people pulling on a rope. In this case, it's not two objects acting on each other. This is two people acting on one rope. So even if the forces might be equal in opposite direction, they aren't part of an actual third law pair of objects acting on each other. So like gravity and normal force is not a third law pair. You sitting in a chair, the gravity and normal force is not a third law pair. I forgot to mention this before, but third law pairs have to be the same type of force as well. So even if you have gravity and normal force preventing an object from falling through the floor, those are not a third law pair. Also partially because, they're both acting on the one object. It's not two objects on each other. One more true or false. Remember, your force isn't the only force acting on any object at any given moment. The floor is going to push back with friction. There might be a wall behind the cabinet with a normal force. If you push a cabinet into its wall, no matter how much force you exert, you're probably not going to accomplish much. So yeah, remember, F equals ma is net force, not just any force. So if there are other forces pushing back, it might not actually move. Honestly, I probably should put this question first and the other question later. That probably would have been better for the overall difficulty curve. I'm not an experienced Kahoot maker, though. I play Celeste for our game for my time with my time. Anyway, yeah, very straightforward F equals ma problem. Looks like a few people just said 10 newtons because of 10 acceleration, but we're looking at the force specifically on this apple here. And in that case, we have a force is equal to the mass, which is 0.3 times an acceleration of 10. So 0.3 times 10 is 3 newtons. And that's going to be the correct answer, which most people did manage to get. I don't remember if Kahoot actually shows which problems were the most missed. If it does, that'll be convenient. But if it doesn't, I'll just try to remember that, right? What does this button do? All right, view summary. Difficult questions. All right, this one's just a bit of another thing where it looks like some people are still having issues with net force versus, like, not net force, like velocity versus acceleration and all those different values that have to matter. It's not exactly easy to try to come up with questions like that whenever. This is something we can look more into. Because this is definitely a lot of you guys missing the fact that time, we're looking for velocity instead of acceleration here. Stuff like that is just something you have to keep track of. Remember, like, keep track of what quantity you're using. Units can be a good way to keep track of that. Although converting from knowing that acceleration in F equals ma is meters per second squared isn't exactly intuitive. And yeah, this one isn't as relevant to like an AP's into like the course as a whole. It's just a good review of being able to understand what forces are which. So we're not going to go over that much. So, all right, if we want a few example questions, I'll put a few in the chat since we still have a lot of time left. I didn't quite plan for there to be this much time. Right. I did think I'd have to go through some of these a little more, but it looks like on the whole, you guys have okay. I'll put the share back on the PowerPoint then. So yeah, we can leave some Newton's second law for now, since that was definitely one of the ones people had some more mistakes with. And there's not much more to see in the full report. All right. So, all right, here's something to start with. Okay, so if you have a 1 kilogram block and it gets pushed on with a force of 3 newtons and the floor exerts a friction of 2 newtons on it, what's the speed going to be after 3 seconds? I'll put this in chat. You guys can think about it a bit. I'll see if I can get more example problems next time, because it does look like just having more example problems might be necessary and just sort of better here. In case anyone missed it, I did put an example problem in chat. Please try to work on that one, and then we'll go over it if people are simply unable to solve this. Oh, participants raised. You don't see anything? Oh, I messaged hosts and panelists. That is. Yeah, I'll call paste that. Sorry, everyone. Maybe excited. Raised hand. I'm not sure if I can create a poll for this. I don't know how to create polls. There's already 8 polls made, and none of them are mine. How do I check the full list of people who raised their hand? Doesn't show me on the participants list. I'm pretty sure you can message me directly in the chat option, or at least just message to hosts and panelists, which should be good enough. So as you guys are getting answers, you can try messaging to me, and if you can't figure out how to do that, putting it in chat works. Keep in mind, the question's asking for the speed after 3 seconds. Always be careful about reading what exactly the question wants to know. That's just a tip for every course. But yeah, it's especially important in physics questions because there's a lot of different values you'll have to work with over one question. Remember, keep units in mind. Newtons is a unit of force, not speed. Questions will ask you to include units, and if you get the unit wrong, you will lose points. So always be careful about what unit you're including. Even multiple choice questions will sometimes put multiple answers with the same number but different units. Always know what unit you're using. Okay, those look good. We have some answers now. I will say it's a good habit to write units in your answer. Get you into the thinking is going to be required a few times. But yeah, the answer is going to be 3 meters per second. So if you want to have this worked out, the first thing to find is the net force for the F equals ma, obviously. And since friction is always opposing motion, you're going to have to subtract the two forces. So you have 1 Newton total. And this is going to be 1 divided by 1 is 1 meter per second square of acceleration every second. And if you apply this for 3 seconds, then you have a change in velocity of 3. And of course, you simply started pushing on the box at when it wasn't moving. So that's going to be a final velocity of 3 seconds, 3 meters per second. It's good to get used to this sort of thing where it might get boring, but also it's just sometimes a good idea to practice the same type of question repeatedly to make sure you never miss it. They don't release the AP exam MCQs, unfortunately, which would be super helpful to actually practice with, but College Board is College Board. What are you going to do about it? On top of that, I'm going to send another question now. Feel free to solve the next one too. Does anyone else have an answer? Or are people still working on the question? Well, maybe wait 1 or 2 more minutes and then, yeah, just one more answer. I'll wait a little more. Not seeing them in our answers, so I'll just let you guys know that the answer is 32 newtons. So the first step here, we're looking for a force, so we're going to go straight for the F equals ma. But to find that, we're going to need the acceleration. And since there was a total change in velocity of 20 meters per second, which happened over 5 seconds, remember change in velocity is acceleration times time. So we're going to divide 20 by 5, and we get that the acceleration is 4 meters per second squared. From there, you have an 8-kilogram box, so you multiply 8 by 4, and you get that the final force that you're going to need is going to be 32 newtons. Right? I do want to try to go for something a little more interesting than just pushing on the box. We'll see about this. Well, we're still going to be pushing a box, but slightly differently on this next question. Those look like you guys mostly understand third law forces, though, so that's good. Make sure you look into that a little more if you're having trouble with that, because missing a third law question is it hurts a lot. So make sure to never try and miss those questions. If you want a hint, note that the box isn't moving, first of all. So what does that say about the net force? I've only got one answer so far, and it's not correct. So start by figuring out the net force and then work your way from there. There's a total of 3 forces acting on this box, and you can find 2 of them with information in the problem. Does look like people are having trouble with this one, though. If you want, actually, this is a good place to start drawing some free body diagrams. Draw the box on the spring. Represent which way the hand is going and which way the other forces are. Feel free to describe your free body diagrams if you want to know how you're doing with that. We're gonna be doing a lot more free body diagram drawing tomorrow, but this is a good place to start. It's a good habit to get into. They can help a lot. So, yeah. All right, looks like most people are starting to get the correct answer now, or at least. All right, so the answer is 20 newtons, but saying that it's a reaction to the force by your hand that's not the best. That's not a good way to think about it. Because you're starting to think that's a third law pair. It's not a third law pair. The third law pair for your hand would simply be the box pushing back into your hand. The spring force on the box is not going to be a reaction. It's simply going to just be because you've pushed onto the box and the spring is now compressed. So be careful where you use the word reaction or just anything like a third law pair, because spring force and normal force are 2 different types of forces. So you will have to be careful about that. Saying something is a third law pair when it isn't is also a good way to miss a problem, just like missing a third law pair. So be very careful about what you say about third law pairs. As for the solution itself, does look like most of you get it now, but the important thing here is there's 3 forces, like I said. There's going to be a 40 Newton force downward of your hand. And then there's going to be oh, did I make a small mistake? Oh yeah, I made a mistake. That's the slide's flying. Yeah, I've made a small mistake. It's going to be 60. That's a Small numbers mistake. Anyway, you have your hand pushing downward, and gravity is also going to be going downwards. The only force pushing upwards here is going to be the spring on the box. Obviously, we're not looking at any other object here. Anyway, you have your hand and gravity pushing downwards, and obviously your hand pushes with 40 newtons. And gravity, like I said, like I put there, we're going to approximate to 10 meters per second squared. You'll see 9.8 as a more common approximation, but in terms of just getting started with physics and just using numbers, 10 is a lot more convenient number, obviously. Anyway, looks like a lot of people might have just divided 40 by 2 and then forgot about gravity. I made the small mistake of drawing gravity the wrong way in my diagram, but 40 newtons is 40 newtons. There's no, you don't change that 40 newtons because in the diagram, in like a sum of net forces, because it's already a value of newtons. You'd multiply by the mass if it was an acceleration. But okay, moving on to gravity. If you multiply 2 kilograms by 10 meters per second squared, you have a total of 20 newtons downwards. And this means that there's a total of 60 newtons pointed downwards from your hand and gravity. And because the box isn't moving, the net force has to be 0. So the remaining force is going to be the other force in this diagram, the spring force that pushes upward, is going to have to be 60 newtons, so that the sum of all forces happens to cancel out to 0. So yeah, it's 4 o'clock now, so that's the end of this class. Goodbye, everyone. I'll see you all tomorrow.